Hello, everyone. All right, so we are now recording. We're going to get started with the class today. So let's take a look at Brightspace. I think you have a homework assignment due tonight, so make sure you submit that, please. And then I think you already have the second homework, and that's due next week or in 2 weeks. 2 weeks from today? Okay, great. That's perfect. Right, so make sure you're working on that. We've already covered that as far as the tools and everything, all the code that you need to kind of do that work. Today we're going to just do theory, all right, but very important theory with code, of course. So some very interesting ideas, okay? All right, so far in the semester, we've gone over mainly large language models, right? So you guys have seen that, and in particular, BERT has been the focus, right? We are using GPTs, but essentially we've looked more at the BERT side. As I've said in 520, we covered GPTs in detail. So we've gone over, Hugging Face transformers, autoencoders, word embeddings, and BERT, fine-tuning a BERT classifier, fine-tuning a GPT, and reinforcement learning through human feedbacks, where we update a GPT via BERT. Two models. Remember this idea, okay, of having two massive neural networks. In fact, three, right, if you remember. There's the reference also, GPT. So, and that's been, that work, that was essentially how they did the first Chat GPT. You had a GPT, create a reference of it. You don't want the GPT that you're updating to deviate too much from the original. And then you had a BERT model that was providing some feedback, right, as a reward model. So that, we've talked about the stages of training a large language model, from pre-training, which, something covered in 520, to fine-tuning here. And then there's a third stage called reinforcement learning through human feedbacks, when we don't actually know how to train the model anymore. All we can do is like kind of give examples, right? Or look at what it's doing at this point and say, I prefer this one or that one, right? So that's the feedback, that's the reinforcement learning. Does that make sense? So those have been the three methodologies that can be used to train large language models, and essentially those are the main techniques. There are other things beyond that, like reasoning and things like that, but that involves also inference, so that's a different kind of a problem. If time permits, at the end of the semester, I may cover that, but otherwise, the topic right now of importance is really reinforcement learning. All right, so we've gone over, fine-tuning a classifier, reinforcement learning through human feedbacks. I gave you papers for you to look at, and TRL, right? So I've demoed this already and demonstrated that it works. The BERT reward function, so we've talked about this in 3 cases as well, right? So you know that. So that brings us really to these two modules. These two modules, you'd be sad to know, kind of bring this section of the course to an end, right? Which is, fine-tuning large language models. Some of these ideas, of course, we're going to continue to use in other areas. But today my plan is to cover this link here. I'm calling it reinforcement learning. It's still related to RLHF. I just have 2 different names, and I wanted to keep these 2 things separate, okay? And this one is a little bit broader, as it covers the theory of reinforcement learning. I should state that reinforcement learning could be a course. Like, we could do an entire semester of just reinforcement learning, okay? So be aware of that. It's a massive topic. Today I will focus essentially on this link, okay? As time permits, I might cover Q-learning later. So there's like 2 areas of reinforcement learning, right? There's like Q-learning, and then there's like policy optimization methods, like two families. So initially what happened historically is that I think in 2014, 15, we got AlphaGo, right? And we got this thing that would play games, would play Atari games, and it did really well at playing Atari games back then. And so that was a breakthrough. It was published in Nature. It's like a big deal. I think there's a Netflix documentary about it. And AlphaGo, it's the game of Go, right? So it's beyond chess. So a lot of this in reinforcement learning has to do with games also, right? So teaching AI agents to play games. So I don't know if you guys remember this, but chess, I don't know if any of you play chess, first of all, right? So chess is a great game, but humans at this point in history cannot compete with AI, or even just any computer. The computers are always going to be better. And yet, chess is a great example of how, even though AI is better at something, that field can still continue. Humans like to play with humans, and that's the reality of it. So there's a lot of chess players that train with AI, but they still go and play with humans and other humans. And so the tradition of chess didn't end because of AI. It's still, if anything, it's bigger now, I think. It's more popular. Magnus Carlsen being the world's champ, pretty good chess player. So anyway, I don't know if you know, but chess was, there was a famous thing that happened between Garry Kasparov. He played a match against something called Big Blue or Deep Blue back in the 90s, I believe. So a long time ago, and the computer defeated Kasparov back then. And they weren't using the advanced techniques of machine learning that we have today, okay? So, but they were using, some ideas of computing. So that's I'm just giving you the history, right? So the history is chess as a game, reinforcement learning uses games a lot. Chess was studied highly in AI and reinforcement learning for a long time, but like I said, in the 90s, humans were defeated in chess by computers. And it wasn't even advanced computers. Then over time, we've had, more complex games. So a more complex game is something called Go. I've never played Go, but it's very popular. It's like chess, but much more advanced. And this required machine learning and reinforcement learning to come in and build models that could, defeat human players. So at some point back in, I want to say 2015 or so, there was something called AlphaGo, probably by Google, and this algorithm, I would say, model, defeated the world's champ, Lou Sedol or something like that in Go. Okay, so that has been evolving. Then there was, I forget, the MNI paper, I believe, that played Atari games. So anyway, back then, a lot of these algorithms were using a technique called Q-learning or deep Q-learning, right? So it's a family of algorithms. But there's also this other family of algorithms called policy optimization algorithms. And so this is another area of reinforcement learning. And as it turns out, even though people have tried Q-learning for LLMs, it was really this family that was the one that contributed to creating things like ChatGPT, DeepSeek, and so on. Does that make sense? So in the area of reinforcement learning, there's at least these two big families. And Q-learning was definitely very popular for a while in 2015, but this kind of took the lead. And today, this is the dominating set of algorithms. This is the optimization goal, essentially, in reinforcement learning through human feedbacks. Okay? And so this is what is used whenever you guys have seen it, right? So we looked at the documentation for TRL for the homework assignment that you guys are doing. And you saw that TRL had PPO, DPO, I believe GRPO was also there, right? So these are the variants of these algorithms, okay? So because of that today, we're going to focus our attention on PPO, okay? So this is what we're going to talk about today. I've created kind of in the same tradition as a baby bird, baby GPT. I have a baby PPO, RLHF. So we'll go over this algorithm, obviously you guys are using it in the background with TRL. It's implemented as a library, but today we're going to try to do this from scratch and just get a feel for how it works. Make sense? So that's the history. So what are these things? So they're not like the inference or the architecture, right? That's usually what we study. We look at a bird, we look at the attention mechanism, all of that, the architecture of the neural network, right? So that's one thing, usually the inference function. But PPO is more like the loss function. Okay, that's what you have to understand. So you know how we have cross entropy, we have MSE to train our neural networks. Even ChatGPT is trained with cross entropy. So think of PPO more like the loss, okay, the thing that we're minimizing, okay, in this context. And it's very interesting how this works, okay? It's a ratio actually, right? So it's going to be very interesting. All right, so yeah, so let's get started. So today, as I said, my plan is to cover this. I do have this other lecture on DeepSeek. If time permits, we'll cover it. Otherwise, you guys can just read it on your own. It's not really technical. It's more like historical of DeepSeek and why it's so important. It's kind of like a blog post that, or just a collection on GitHub of things that I've been putting together. This is relevant because they propose something called GRPO, right? And it's obviously it's PPO but with extensions. Okay, so they have several nice papers, and like I said, one of the key important things about DeepSeek is that whereas OpenAI was not really disclosing everything that they were doing with ChatGPT, so they disclosed up to a certain point, and then they were keeping it as a secret to their company. But then eventually we got DeepSeek, which is just as good, and they disclosed everything, right? So we then know, okay, we know what's going on. All right, so let's take a look at reinforcement learning then, and let's take a look at this material. So as I said, there's several things here. I provided this paper. This is the Siegler 2020 paper, so you can see the date there. This paper, so it's called Fine-Tuning Language Models from Human Preferences. So whenever you hear the term human preferences, that's reinforcement learning through human feedbacks. People call it preferences, things like that. All right, so this is OpenAI actually did this work. So you can see up until then, they were still disclosing things. This is before they revealed ChatGPT in 2022, if you remember. Important, I don't know if you guys know who this person is, Dario Amodei. You guys don't know who this is? This is the, what do you call it? The CEO of Anthropic, the Claude, that's him. And so it's a very important person. All right, yeah, so if you read the document, obviously I will explain the code in a very brief way, but it should be correct and should work. But read through this paper. I highly recommend that you read it. You can see here, it's already, kind of like how I did, it starts talking about Q-learning, right? So everybody starts talking about Q-learning. This was the very exciting thing in the beginning, right, of like 2015 and so on. Let's see. Yeah, and so it'll explain kind of the difference between these policy-focused approaches and then Q-learning approaches. And then it'll talk about that. I was looking for the paper because I can't remember. There's an Atari. It's driving me crazy, though. Q-learning Atari paper. It's got to be something like that. Yeah, I think it's this one. What year is it? 2013. Yeah, MNI, this is what I was looking for. So you can see it's actually earlier, and they did this Atari thing and the underlying Q-learning, right? So, and then AlphaGo, I want to say AlphaGo was also, and there's a Netflix documentary on this one. AlphaGo paper. Yeah, it was on Nature. So it's a huge difference to publish on whatever the other one was on, even NIPS or IEEE or something, versus publishing in Nature, right? So, okay, take a look. David Silver, who is a highly known person in reinforcement learning. See him there. Mastering the game of Go with deep neural networks and tree search. Go. Yeah, mastering the game of Go. So this is possibly the AlphaGo paper. So you can see policy network. So I don't remember if this one used Q-learning or policy approaches. But this was, yeah, it's like a chess game. But this is a very important historical paper back then. Okay, so, but as I said, this was the focus. Reinforcement learning still today is used in games. Okay, now I should say that you can create a game for a large language model, right? That's not a difficult thing to do, and in fact, the same idea applies. So I don't know if you guys understand, but the beauty of reinforcement learning is that you don't have to annotate data, right? You know, instead you create a game. So what you do is, if you create a game with constraints and points and win, lose, then you unleash anything on it, including a GPT. So the GPT does something, takes actions, gets feedback, and it learns. Do you see that? So essentially, that's a really nice solution to any problem. You can even say that if you can take any problem and convert it into a game, right, then you can train an AI to learn it. I mean, you could create a game of physics and teach a GPT to solve physics. You know what I mean? So it's kind of like that. All right, so these are the papers historically. So this one, AlphaGo, is really important because of, as you can see, it published in Nature. So anyway, that's kind of, 2016 and so on. So then we have the PPO based algorithms. So we're going back now to our GitHub and this important paper. So let's take a look. Reinforcement learning, Siegler 2020. And as you can see, they're essentially fine-tuning large language models from human preference. So you can go through it, and, all the ideas. We're going to have some terminology like policy. Policy essentially is going to be the GPT in this context, okay? And then there's going to be a reward model of some kind. So you've seen that already. A BERT is a reward model. GPT is the policy, essentially, right? So we're going to know that terminology. Read through it, but if you look through the text, and this is what I'll describe today, so don't worry about that. Read through it, you can see it starts to say that they use PPO, which stands for Proximal Policy Optimization. Okay, so this is essentially a seminal paper, right, that was happening there. Notice that there's this idea of the KL divergence, so we need to talk about that as well. Okay. And, they provide the results, and the model, obviously, it did work since we have things like ChatGPT today. Okay, but I strongly recommend that you guys read through this paper and, get a feel for how they reported things 6 years ago. All right, so now that I've provided the paper, we can start getting into the algorithm of PPO. All right. Because it would be very complex, to look at all the algorithm in the context of TRL with a BERT and all that. I have simplified a lot of things, right? So I've followed this approach of the baby GPT, and so I have a baby RLHF, PPO, and so we're just going to get some of the ideas of how it works, okay? But it's got all the math principles. So let's take a look here now at this one. So it's going to be PPO, so we can jump here to our GitHub. And I'll be using Colab to go through this one and so on. and we can work through it. All right, so here it is. So I have this repo on reinforcement learning, and there's a lot of things in there, but really it's just this submodule on theory, right? So this is the one. So I'll go over this. This is the code, essentially. I did provide this README, because there's a few things that we need to understand, and for some of you, this is, you know this already, but we need to talk about it a little bit. So essentially, one of the things that we have to understand, the model is kind of learning from how it's predicting now versus how it predicted yesterday. Do you see what I'm saying? That's essentially what's going on. Like the optimization is like that. Like in regular supervised learning or something, SFT, what do? We have the model predicts and we compare to something real, take the error, back propagate, right? You guys get that. Here, you know, we don't have that, right? And instead, what we have is we have this idea of a reward, but the model essentially is I'm predicting today, and I also predicted yesterday. So I'm going to compare just that, and I compare it through a ratio, okay? So it's like a ratio, A over B. And that's the optimization that I'm trying to do with a few additional parameters going on in there. But that's it. That's like the heart of it. Do you see that? All right, so yeah, go ahead, please. That's there's a goal of the framework that ratio should not change too much, and you're like a little bit better. So we'll see that. But it's a minimization or maximization problem of that ratio, given a reward. So you'll see. But essentially, in essence, that's it. Okay? It's like before we compare predicted to real, right? Here we compare my prediction today versus my predictions before. It's just not today, but now and before. Now and before. Okay? So let's take a look here. So there's one trick that you probably know about already, but you know, I'll mention it. So this is going to be the code that we're going to discuss, and we're going to go through it slowly and just kind of get a feel for what everything is. But there's this. And for those of you that are experts in math, okay, this is not a derivation or anything, so I'm just showing you some specific things, okay? So the logarithmic representation of a ratio. So this is a common thing in machine learning. You probably have seen this in naive Bayes and other algorithms, you know, or the residual that you learn in 520, right? What was the problem of the residual? As it gets deeper, the probabilities get tinier, right? So 0.005 times 0.005 becomes 0.0005, right? So at some point it almost becomes zero, right? So there's a solution for that called a residual, or there's tricks like converting something to log space so that instead of being like a multiplication is an addition or something like that. Does that make sense, guys? So that's why sometimes you hear about the ratio, but then you look at the equation, it's like, this is not a ratio, so it's confusing. Another thing that's confusing is you see an R and it says ratio, but they're talking about rewards. So be careful with that. It's, you know, you'll think it's a reward and it's not. So we have this trick, right, that you're going to see in the code. So we have the logarithm of a ratio is the difference of the logarithms. So essentially, even though I'm going to say that it's A over C, right, the new probabilities over the old probabilities, and this is the ratio that I'm trying to optimize, when you look at my code, it's going to be this, right? So subtraction. So you're going to see A minus C, but in the log space. Does that make sense? So that's essentially the trick, okay? That's very common, and this makes the formulation and the model more stable so that it can actually learn. So the identity holds for this, so in the different bases. So why is this useful? It simplifies division. So instead of dividing values directly, you can subtract their logs, okay? Questions? I mean, I'm not going to derive it. I mean, it's like it exists. It works like that. So what I'm saying is this is a math formula that the log of a ratio can be represented as the log of, a ratio of AC can be represented as the log of A minus the log of C. That's right. It's not the exact value, but it is equivalent. So that you can do it in this, and the answers are the same as these, but this is way more stable. So that this happens also in multiplication. So if you have A times B times C, that can be log of A plus log of B plus log of C. It's a set of rules that exists. Does that make sense? Yeah. Yeah. So this is just, math. You're the math expert, right? So, yeah. So, yeah, it's true. There we go. Done. So, yeah. So, but what's great, sometimes what's confusing about some of these algorithms is that, as I've explained with the residuals and everything, right? Things get tiny, they're unstable, but by doing these little tricks, now it's much more stable and the model can actually learn. All right, so anyway, whenever you see in my code log of A minus log of C, just remember it is actually the ratio of A over C, okay? All right, great. Yeah, so why is this useful? It simplifies division. So instead of dividing values directly, you can subtract their logs, okay? Used in log transforms, often applied in data science and machine learning to normalize ratios. Applies to probabilities also, so log-like likelihoods, and on Bayes' theorem. So this is used in Bayes, like naive Bayes, for instance. Here's just a simple example of the calculation. You can take a look at it. Sometimes, like I said, these values are not the same, but they're equivalent, right? And that's really what matters. Okay, so here's an example just for you to play with if you'd like, but that we're just going to hold this as being true, okay? And here's more relationships. Like I was saying, A times C is log of A plus log of C, and so on. So these are just conversions. All right? Yeah, so you can use these rules when simplifying log expressions, implementing log space math, or working with numerical stability in algorithms. And as you know, with machine learning, this is a key problem that we have to deal with. Okay? So that being said, all right, you can see now that in the code, there's going to be this. Do you see this here? New log probs minus old log probs. But that is the ratio, okay? Got it? All right, great. So if you understand this, then you'll understand pretty much everything else. Should be very clear. All right, so now, so what we're going to do now is I'm just going to go over, this is the baby RLHF PPO. It's only PPO, okay? But we're going to try to understand how it works. It is a super simplified version, okay? I've covered this already. This is actually the code that I will be using. I did provide some additional comments, and feel free to read through them, just more explanations of how things work. And I will try to mention some of these as we go through the code. This is the PPO code. I do have some, now, as I said, so imagine there's this idea of proximal policy optimization, right? I said to you guys, and this is the loss function essentially, right? And it's a ratio. But over time, people are creative, smart, so they have taken PPO and they say PPO is great, but how can we make it better? So over time, they have created various versions of this. The most important ones, in my opinion, are DPO. This one is really interesting. DPO gets rid of the reward function or the reward model. Think about that, right? So you go from having the policy, the GPT, and the reward function. That's a lot of memory. And they mathematically said, we can throw this one out. We're going to use this idea of like preferred, dispreferred. And, so obviously it's going to be our PPO, but modified for this idea of DPO. Yeah, yes, sir. That there is no reward function. Yeah, it learns in another way. Yes. Make sense? This is a paper, by the way. I didn't include it, but if you want to read it, it's a Stanford paper from like 3 years ago. It's one of the biggest contributions from academia to the world of LLMs because, you know, LLMs, everything that happens, all the research really happens at some company, right? Because they have all the resources. But that DPO, the proposal of DPO, was actually done by the professors at Stanford University who they actually just did the math. They went into the math of it. They like solve for X, you know, that kind of thing. And they just went like this, and then they found out that the reward function canceled out. And so they stated everything in terms of just the model. But I'm not going to cover this one today. You can start reading through this code if you'd like. But this is the DPO. I'm only focusing on PPO today. So that's why this is novel, DPO, direct preference optimization. SPO is just a variant of that, very similar. And then there's GRPO. This is generalized reweighted PPO. Okay, this is the one proposed by the DeepSeek paper, and that came out like in the last 2 years, I believe, state of the art. And so I think you saw in TRL they've now added it, right? So this had something to do with an average reward. So I haven't read this paper in a while, so we'll come back to that topic. All right, make sense? So these are just additional, these are kind of my notes at this point. So I'll come back to these, but the focus today will be on PPO, and just be aware, PPO is a bit dated as it's been, you know, this area moves really fast, but the concepts are still like the same. It's just there's an improvement here and there, okay? All right, and I can tell you the goal is to remove that reward model because it's complex to have two neural networks and things like that. All right, so now that we've mentioned that, let's just go in and start looking at our PPO code. So I have together this, just my notes. You can find this collab here at this link. All right, and let's just start building. It is probably the best way to understand this is to just try to build this little baby RLHF PPO. I don't have any, it's not pre-trained or fine-tuned. We're training it, you know, it's just an inference really model, no data. So I'm keeping it very simple, right? Very small footprint. All right, so let's add the library. It is in Torch, so it's the very classic ideas. All right, so Torch, TorchNN, Optim, so right? So we have that. We're going to have the notion of two functions. One, it's the GPT or the policy, right? And the other one is going to be the reward function, which in this case, the reward function can be anything, can be humans, can be a heuristic rules, or it can be a neural network, right? But we're just going to keep it simple. In this case, is an if statement, all right? Just to keep it pretty simple. All right, so I added the libraries. All right, so now if you notice, I'm going to grab this. Yeah. So there's two things here. One is the policy. The word policy is usually like symbol pi. That's the policy. But here it represents the GPT. Okay, just keep that in mind. Obviously, you can see it's a very small architecture, so I'm just producing like an embedding, a simple token. Does that make sense? Just to kind of give this idea of generating language. Okay. So, but it's all going to be just the embedding. So you can see here I have a tiny GPT style policy. Okay. So what needs to happen is the model gets a prompt, right? So which is the input, produces an output, and that is used in the context of the reward and so on. Okay. And we need to keep track of old predictions and new predictions. Those are usually going to be referred to as the log probs or the log probabilities. So notice here, vocab size is going to be 10. The hidden dimension is just very simple. Just a simple neural net simulating a GPT. Okay. Hidden dimension of 16. So you can see here the model takes in embedding of or vector of 16 goes into a dimension of 10 goes into a dimension of 16, and then from 16 it goes to a vector of 10 for the vocabulary. Okay, so I'm using the NN embedding, and then I just have a linear which simulates a head. Remember, we've talked about this idea of heads from embeddings to whatever it is that we're producing, whether it's a score or something like that. All right, over here in the forward section, we're going to have the input IDs, right? Whatever the ID is, we take those and we're going to embed them, right? So we should have a sequence of 10 with the embedding size. Then we grab just the, X, whatever the last embedding, okay? And then we run it through LM head to produce the vocab size. So we'll test this out in a little bit, but you can see the idea, okay? So this is, in our context, the GPT. Make sense? All right, so now let's take a look. The other thing that I have here is the reward function. This one is super easy because really all we need is some kind of a score, right? So essentially, this reward function just says return 1 if token is 1. So like if I get out of the 10 the token 1, then it just gives a plus. Otherwise it's 0. So fake reward is, it's just a made up reward function here to kind of show the functionality. Okay. So the torch where is like a if statement, right? So if token ID is equal 1, then the reward is 1, else it is 0. Do you guys see that? So that's in line with what reward models produce. Obviously, this could be a BERT. This could be lots of different things. But it doesn't have to be a BERT. My understanding on the DeepSeek paper is that the reward functions are based on heuristic rules. So there you go. All right, so, but yeah, that's the reward function. Then this is PPO. And PPO, oops, sorry, I think I did that. PPO can get confusing if you start reading and then you start seeing things that don't make sense, like I said, but actually it's not that complex. So let's take a look. So here, take a look. So essentially you have the PPO loss function. Notice here you have new log props. So what is that going to be? Think of it as a prediction, the new one, right? So the GPT or the policy or whatever it is, because this could be also for playing a game, right? You could use PPO for, I'm sure, to drive one of those self-driving cars, for instance, something like that. So what you have to understand is that it's predicting something, and it's in the log space as we described, and we just call it the new log props. But you also have an old prediction, so that's the old log props. And then you have, for every time that you do that, because it's a ratio of new to old, you also have a notion of a reward, right? Sometimes this is called the advantage function for some reason, but it's really a type of a reward or an approximation of a reward. And then you have this KL coefficient, which we've talked about already, the KL divergence, as it's called, okay? And I think I described that to you. It's a function from information theory that compares two distributions, and it tells you how close they are. So you can think of the GPTs, the policies, and what they produce as a type of distribution. So that then allows you to say, well, I want my model not to deviate too much from the original. Do you guys see that? And the KL divergence then makes sure it's like a constraint, if you're familiar with that term. So you can see here the general idea. So we have the new log probs, the old log probs, the rewards. And notice over here that we have this strange thing called a ratio that is not a ratio, right? And so this is what I was saying before. So this is where this would represent, like in the paper, it may actually say something like that, but it's not in log space, right? So now you can see here, new log probs minus old log probs, but that's the ratio. Make sense? Key point. And it's called ratio, not a reward, right? But just a ratio. Then over here, I have the next part of this, which is the ratio times the reward, the reward that I was able to receive. Okay, so it's like a weighting mechanism for the ratio. Okay? Do you guys see that? All right. And I omitted this part, but there is actually like a function where you say, I use this or my alternative, and my alternative is the same as this with a clipping constraint. And what that means is you want to clip that ratio. For instance, intuitively, I can tell you, I don't want that ratio to be above 1.25, or I don't want that ratio to be below 0.85. Do you see what I'm saying? If there's a clipping that happens, I omitted that here for simplicity, but just be aware of that. So it's like choose whichever one is better. If it exceeds, do the clipping. Or if it doesn't exceed, then use the actual value. You see that? So that's in the paper that go ahead and you should read. All right, so then I have the ratio, I have the rewards, and now this surrogate over here, right? That's it. So notice then that I'm going to take the surrogate over here, like that, and keep in mind the values would be several values like a vector, so you can take some single number, like a mean of it, but there's an additional thing here. Notice, I am taking the ratio times the reward, I'm calling it surrogate, that's this part over here, and then I have plus something. So usually you guys probably remember from 520 when we had a loss function, we have MSC plus something, right? Or cross entropy plus something, and we call that term the regularization parameter. So some kind of an additional thing, or it could be, if you're neural input optimization, you had, 1 plus, so you can add terms. So this here represents the KL divergence. I'm not using the actual formulation of KL, but it's called, for those of you that are interested, it's in the paper. It's called the Kullback-Leibler, I believe, regularization or divergence. And essentially, as I said, it's just a metric that compares distribution. So in this case, to keep it simple, we're treating the old log probs and the new log probs as the distributions. Now keep in mind here, this is not meant to be a ratio. This is just a convenience to take the difference between them, okay? But this could be elaborated more. And PyTorch, for instance, has a function called the KL divergence, which takes two values. So we could use that. Got it? But this just keeps it from scratch. So keep in mind then, and then there's this coefficient to kind of give a weight to how important that is. This actually is really important. This is how you control how much you want your model to deviate, right? So let's say you're building, and we might cover this a little bit more when we look at the time series GPT, but maybe your model is just like deviating too much, right? So then you constrain it more, so that you could make this dominate so much that it totally ignores this, for instance, right? So that can happen. Does this make sense, guys? So this is the actual total formulation of the PPO. Okay, so with all the terms that are important. So I have some notes here. I'll write it how you see the equations, but essentially that's what it is. So here, your ratio part, then times the reward that's provided, that becomes this surrogate. You calculate some kind of a mean, and then plus the KL divergence control, which essentially is keeping, and here actually, I don't have this, right? But it really should be like how we did it in the TRL example. If you remember at the beginning, I downloaded the GPT and I just called it Ref GPT. Do you remember that? And then I took the other one, and that's the one that was updated. So technically speaking, this old probs is not actually like the current one. You would want this to be like the one at the very beginning. So let's call it old probs, like 00. And that becomes like at the very beginning, you take that one because that was before you started doing the training. So you just want to keep it, not deviating too much from where you were before you started the reinforcement learning training. As the models can definitely deviate completely. So you have to have some kind of a break for it. Does this make sense, guys? So that's key, right? So I would have needed to add more code for this, but just be aware of that. Questions? That's it. So obviously we're going to implement like the logic of it, but that's essentially the whole idea. All right, so a ratio times a reward plus the KL divergence. All right, and so now let's go ahead and make sure this runs. Okay, so we have that. Now let's kind of take a look at the idea, just walk through it. This is not trained, obviously, so it's just going to give us some values, but just to kind of show you the workflow of it. Okay, so here the training loop, so this is going to be our parameters, the vocab size. We instantiate our tiny policy. And I want to stress this is the GPT, but we can call, the term in this vocabulary in reinforcement learning is policy. And then if you notice over here, you probably understand this part, right? This is the part where we tie the weights of the GPT to the optimizer. So essentially, we know then that the thing that's getting updated is the weights of the GPT. So this is how we shift the weights of our pre-trained and fine-tuned GPT based on the feedback. Do you guys see that? And so that's essentially the idea. Okay? Some kind of a learning rate is provided, and we call this the optimizer. Okay? So this is familiar to you guys as you have done this extensively. And remember, this makes sense because the thing that we want is we want to make our GPT be like a fishing GPT, right? Or a funny GPT or something like that. All right, so we run that one. Okay, so we got a check. We're going to go through some of the printing, some of the sizes and things like that. I tried to keep this like, use the word prompt, although there's no real prompt, just like, some IDs and things like that. Very simple, but all right, so we can think of a tensor, 0 value, start with a fixed token. Usually this would be like beginning of sentence token, something like that. You think of it as a prompt, and then there's going to be a generated also, okay? So we can think of it that way. So the GPT. So this is where the GPT would get a question, it provides an answer, and then the question and answer get a reward, good answer, bad answer, and so on. There is no context here of preferred, dispreferred, or bad, good, like in a binary case. This is supposed to be more broad, okay? That it's not just this or that. It could be more options. Mm-hmm. Well, the reward could be a value, right? So the reward could be like a 0.6 or a 0.7 versus just binary, preferred and dispreferred. I mentioned that because the other ones are more like that. That has been like, I think that has been shown to be somehow a little bit better. But we'll talk about that. All right, so let's take a look at, so here I have the old, some lists. So let's try these. So you can have, for instance, I think GRPO generates a whole bunch of questions and answers, then it scores all of them, then averages them, and that's better somehow because you looked at like 64 all at once. And then other ones, just like it's binary. This one is good, this is bad. So that's kind of the difference. All right, so a list of the rewards that you collect, a list of the old log probs that you get. And this is interesting because when I was thinking about GPTs and how the feedback was provided, right? So I would always think of the strings, the words that you get. And it's really hard to tell, okay, how are you using those numbers? But if you remember, before the words, what do we have? Probability distributions, right? Do you guys remember? So the head projects the embedding to what? To a softmax vector of the vocabulary. Do you see that? So that's what you can think, and that's a probability distribution, right? So that's actually the part that we're using. Do you see that? Those numbers. Okay? So, but log probs, because and they're the log of it. Right? So we got the rewards list. Let's take a look at the prompt shape. Okay, so size 1. All right, so I'm just going to look at several parts of the GPT just to kind of get a feel for what's going on in the dimensions. So and then I'm going to use the actual whole thing. So here you can see NN embedding, so vocab size of 10, 16, so I'm creating an embedding, okay, just to see what happens from input to output, right? So we have a sense of what's going on. And then the LM head, so these two parts, right? You understand that there are these two here, right? So I'm just printing them so I can see everything. So the LM head, this one is of size 16 back to vocab size to predict the next token logits, right? The logits are those values. Okay. So if I take this section here, okay, so I have my prompt, whatever it was, I think it was 0, that's an ID, and then I bring this in here to the embedding to provide an X, right? So now I'm in the embedding. Printed. Let's actually print the shape also. You can see, so I'm essentially, it's 1 comma 16, right? That's the size of the embedding. Some numbers, of course, but this is the mapping of the IDs. Then this is just grabbing the last layer. I only have one layer. Of X, right? X, I just grab the last embedding. So there you are. And let's print this one. It's called last hidden. Right, so it's 16, so the same thing. And now we're going to run that one through the head to get a feel for that. All right, so I take this last hidden, size 16, goes in, produces the logits, and I'm going to print the shape and the values. So essentially a vector of 10, right? Probabilities, essentially. Do you guys understand? So I'm getting what? The probability of being one of the 10 words, correct? All right. As I said, super simple, but it does, you agree that it does capture. It just doesn't have the whole N and sequence and all that. Okay. Now, we can use softmax here. Okay, so I grab these logits on the last dimension, and you can see now the softmax does what? It makes them so they add up to 1, so I have a probability distribution. So in this case, the probability would be what? Is it the last one? 20. So this one, right? This token, 9, I believe, that's the ID that would be chosen. Do you guys understand? So that's essentially a super simplified GPT, but it still actually does have the mechanism that we're looking at. Now, what I was saying is, when I was trying to understand this, right? Here in the large language model, we would pick ID 9, and then we'd use the tokenizer, and it's cat. And that's it. And I was like, okay, how do we actually do this computation? Because it's numbers that we have to provide. So actually, you don't do the part of finding the tokenizing the word. Instead, you use these values here. Do you see that? That's essentially, that's it. That's the value that is. And this is actually used also in the GPT, or if you're building a model of your own, that's what you use. Okay? Got it? Yeah. All right. Perfect. All right. So now, and it works like that. That works because, why does it work actually? Because we look at the new predicted versus the old predicted, but the new predicted was still producing, in this example, a vector of 10 probabilities, and before it was predicting a vector of 10 probabilities. And all you're saying is, I like these better than that. Do you see what I'm saying? Like, say I build a very simple one that I always wanted to say cat and apple, right? So it's going to say tiger and orange. And I say, no, I don't like that. Okay, dog and banana. No, I don't like that. And eventually it starts saying cat and apple, right? And I start saying, I like that. So you can see how that works. You're getting those numbers here to start predicting cat and apple. Cat and apple, you give it a higher reward, and that's what you want. Do you guys see that? Does that make sense? So that's the whole game, essentially. All right, you control it like that. And it works. What can I say? It works. All right, so now I think we all understand, right? Like, this is what the GPT is producing, and these are the values that we're going to compare in the ratio. And we know for sure they have the same dimensions, the exact same meaning, because they're literally just the previous prediction and the new prediction. So there's nothing incompatible there. It's perfect, in fact. All right, so now that we've done this, there's another little trick that I need to mention. And this is just something that happens in reinforcement learning all the time. So let me give you the classic example that everybody says from self-driving cars. You could get from here to Chicago probably by just turning left. So you go and you just turn left. Your goal is to get to Chicago. But if you keep turning left, somehow, maybe in 2 weeks, you will get there by just turning left. Do you see what I'm saying? It's possible, right? I think it's within the realm of possibility. If you have a complex network of streets and things like that, just turning left, somehow you go, I don't know, something, right? It's the example. So, but you should turn right every now and then, right? So that's the idea. So believe it or not, reinforcement learning models sometimes make that mistake of just turning left. And so that's called exploration. The technique is called exploration, which means that sometimes you got to force them to turn right so that they experiment in that realm. And then now that they're turning right, yeah, they're going to learn to turn right. And that might be the best approach. So that you have to do that, right? And so in all reinforcement learning, you always have some kind of a little trick that initially, like in the first 25% of the training, 80%, no, let's say 20% of the time, you just pick values randomly. You guys see that? And by picking those values randomly, it's like you turn right. And so that way it can explore the environment and it can get better at it. So in this example with PPO, they use something called a multinomial, which adds a type of a controlled randomness. And this is over, simplified here, but it should do it. It's actually like in, oh yeah, no, you guys didn't cover it. I didn't cover that with you guys. But it's just adding randomization. So it's very simple. So imagine I have this here, right? So we know from the softmax, the word that I would always pick is the word with the highest value. So in this case, I would pick 0.24 as the highest probability here. So I would pick ID 9, right? All the time. But instead of doing that, you run this through a function like this multinomial. And what happens is every now and then, it's not going to pick 0.24. It kind of randomly will pick another one. Do you see that? And the goal is that then that adds this component of randomness. Do you see that? That's it. All right, and so again, just so that it learns that sometimes it should try other things and not get stuck somewhere like, always turning left. So here in this example, torch multinomial adds this controlled randomness. Usually it picks the high probability tokens, like index 9 in our case, but sometimes it will explore others. And this is perfect for this idea of exploration versus the argmax. So we always use the argmax. That's how we learn with softmax, right, in a GPT, but we do want it to explore sometimes in this context. So it's almost like, it's going to get stuck on saying things that it learned about the GPT, right? You want it to speak like Shakespeare, but it always just speaks like the Wall Street Journal, right? So it needs to then get some other term randomly, and hopefully as it's doing this, there's going to be a feedback that says, oh, this is good, and now it learned. Okay, so that's essentially the idea. So that's just a comment. So this is implement. So you'll see this in the code, so I made a note so it doesn't confuse you, that what we're doing is adding this randomness. And Q-learning, if time permits, you'll see Q-learning also has this randomness component. It has been shown with reinforcement learning. This helps out a lot. So you can see here the idea, I take the probs, right, and I run them through here, and the way that it works, it'll create this effect for us, okay, every now and then. And there's lots of other ways that you can do this, but you have to use an approach that is differentiable. You know what I mean by that? That it can backpropagate, essentially. So that's the trick. You can't just use a technique that breaks that backpropagation. And that's a common thing in deep learning, that there's a lot of functions that provide the same thing that you want without breaking the differentiation. All right, so there we are. So essentially, though, it just picks an ID, and sometimes it picks it random. All right. So I picked an ID, right? And then from the probs, I have the value. Okay, got it? So yeah, go ahead. What do you mean? Here, so the GPT does what a GPT does. It's got a softmax probability distribution. With an argmax, then it would pick the ID that has the highest probability. So remember, our vocabulary in the GPT used to be 50,000 subwords, right? And then we would pick that one. Yeah. Mm-hmm. To provide the reward? I'll show that in a second. Yes, I will show that in a second. But actually, so there's various ways that you can do that, right? We learn in the BERT. If I was, let's say I could be using a BERT reward model here without a doubt, right? But it would just take, I would need Hugging Face to do that. But there's several ways I could do this. I could take the prompt, 0 in my case, and the answer, 8 in my case, concatenate those two. That's equivalent to getting a whole paragraph question and a whole paragraph output. Do you see that? same thing, just that one would have had sequence 40, comma, vector of 50,000. My sequence is 1, vector of 10. But it's the same idea. So then I could have taken, but to keep in this context, I could take prompt 0, response 8, concatenate those two, give them to a BERT, and the BERT gives me the reward. Does that make sense? Yeah. Or I could just give 8 and get a reward. Because so remember, a reward can be a person. Like I could have this in real, let's say you build this application, you're in your office, and every hour you get an email with just 2 buttons. And it's your model saying, which one of these 2 do you like better? Click, boom, gone. So you sent that back to the model, it gets the feedback. Do you agree? So that's can definitely happen. In fact, in the original paper, they were kind of thinking like that at that point. Or it could be a BERT, as I described, that provides the reward in real time. Or it can be an if statement. Like, a heuristic rule, right, in a function just means if this or that. That's what I'm actually using in this example, but just to give you context, DeepSeek, according to them, they used a reward model that was based on heuristic rules. So it can be lots of things. At the end of the day, you just need the reward. Make sense? Yeah, great. So good question. So here you can see for the ID, I have grabbed the probability. Okay? There we are. Now, notice over here what I'm doing. The so-called log probs, right? And you see this, and everybody, it's funny, log probs this, log probs that, and you see it throughout the paper. For some reason, they say this, but essentially, notice what is happening here. Right? So I'm grabbing the probability over here, I'm running it through torch log, and you can see the number has now changed. So usually, this probability is actually well behaved, right? 0.06. But that could easily be 0.00006, right? And then as you start multiplying these things, they get even tinier and tinier. Imagine the ratio between one and the other, right? Log probs does this thing where you get these values like 2 point something, so it's a little bit larger. So that's also good. All right, and the formulation changes to subtract instead of a ratio. All right, so yeah, so that's essentially that part. Okay. So we did that, and then essentially you can collect these log probs. So this is another part of the code, just to create a list of the old ones. So this is a super simplification, but it captures the idea. Do you see that? The old one. That's what I predicted yesterday, but now I'm predicting this. And that's the optimization. It seems like crazy that would work, but that's so it's just looking at itself, right, in the prediction. But you have to have a really good reward, right? So obviously this is key. The reward needs to be pretty good, such as a BERT that's really smart, or a human, or something like that, or a really good heuristic. Anyway, so I've recorded now. So you can think of it as the prediction. Now this becomes the old one to keep, and now I'm going to go ahead and go into a new one, and so on. All right, so that's done. All right, next token was the ID, I believe. So that was 8, I think. Yeah, 8. Now here's my fake reward. Okay, so remember, you guys have asked me questions about the reward. Let's take a look at it. So I'm invoked. So essentially what happened here? The GPT got a prompt. It did its GPT thing, and it predicted a word, right? Or it got a question, and it produced an answer. Whatever it is, that has happened now. So now, as you had asked a question, if I was using a BERT, I could take question and answer, concatenate it, give it to the BERT, get back a reward. Because this is super simple, right? I've said I just want a reward. So I get a 1 if the picked ID is 2, let's say. So if you pick 2, you get a +1. Anything else, you get a 0. You see that, just to kind of show you how this works in a very simple terms, but that can be quite complicated. So let's change it. Let's go to the reward. I think I was using 1, but let's change it to another ID. So you see here, I'm just saying, so let's change it to 2, right? Okay, so I load my reward. And now I print it, and notice it gives me a 0. So I got a 0 reward. The only way that I can get a good reward is if my number is 2, my ID. So that's equivalent to me saying, I'm only going to give you a good reward if you give me the word cat. If you give me any other word, you don't get a good reward. Do you guys understand? That's the key insight here. Okay. Any questions on that? Yes, please. Well, I mean, you have to provide a reward. Every time. Oh, I see. Well, I'm going to give it this reward. I'm going to give it 0. This is just an example I invented here. Like, it could be anything, right? So the reward could be a 0.5, a 0.6. I get your point. That it's just 1 versus 0, so it's not. So obviously, your thought is this should be better, right? This reward should be better. That's why if we had a BERT, if you remember the BERT, which one was it? The phishing, I think, that we did in class, right? It did give us a value, right? Or the sentiment one, it did give us a value, right? So you would provide that value to PPO. In fact, we already shown how it's used. It is multiplied. So you're almost weighing the ratio by this reward. Do you see that? So this is important. Okay? But that's the idea. So essentially you're saying this becomes 0 all the time because I'm giving a 0, and then sometimes it becomes a 1 when it's a cat, right? So the word that we wanted. And then, yeah, that you're right. I mean, that's how it works. Yeah. All right. Good question. All right. So I'm going to go back down here. Okay. Oh, yeah. So I provided, so I guess, I don't know if like the syntax, because I think this requires a tensor. Yeah, it requires a tensor, so this may not work, but yeah, but you know, right? If it was a 2, then I would get the 1 as the reward. All right. So I would have to like maybe torch dot tensor, and then I'm going to give it a 2, right? Let's see if this works. And then temp. So if I give it temp here, yeah, it works. So if the ID is 2, then I do get my reward of 1. But we're going to switch it back to next token over here. And so on. All right, so it's 7:49, 7:50, right? So I'll stop this first half here. Let's take a 10-minute break, and then when we come back, we should be able to finish up this in part 2. Okay? Good? All right, so let's take a 10-minute break, end this video here.